study about single conductor, and then we will study about the two conductors, two single phase conductors, and then we will go for three phase conductors. So first of all, we have to know that why transmission lines have inductance, that why they have inductance. So as you know that we already know that when current passes through any transmission line, when current passes through any conductor, that it will link a flux through it. We know about Faraday's law and Lenz's law. Whenever there is current, there is magnetic field, and due to magnetic field, we have flux. So that's why we have our transmission lines have inductance. So normally we denote inductance by L, and it depends upon the length of line. So if we increase the length of line, the inductance will increase, just like resistance, that it increases with the length. For example, if 1 kilometer, for example, have 2 millihenry inductance, then 2 kilometer will have 4 millihenry. We will just multiply by distance. So this is the important point, that inductance depends upon the length of line, of transmission line. So its unit is Henry. I think you already know about this. This is magnetic flux, because I showed you this because you must know about the mu, that what is mu. Actually, we know that the flux flux linkage is equal to flux density multiplied by area. So here, if we will calculate the flux density, so here comes mu. This depends upon the type of conductor we use. So normally we use aluminum conductor. So we must know about the mu, that why we are using mu in our problems, because you must have seen this mu before, and we will discuss this mu in our coming slides. So this is the actually the permeability of conductor. So mu is equal to mu naught into mu r. Mu r is relative permeability. So normally we take it as 1. In future, our problems, we will take it as 1. So normally we will take mu is equal to mu naught. So we will solve this, and then you will understand better. So for example, first of all, we will study about the single wire inductance. So for example, I have this conductor. If I will see microscopic view of this conductor, and this blue line indicates the flow of current from a conductor. It can be a single conductor, any single, because to know about the two-phase transmission line inductance or three-phase transmission line inductance, we must know about the inductance of a single line. After that, we will understand that the formulas and the relation of inductance. So first of all, for example, this is conductor. You just see this part, okay? I will explain this later. So there is a conductor, and current is flowing from this side. So if I want to find inductance at point A, so how I will find? Now I will tell you. So this is the D is the distance between the center of line to the point where I want to find inductance. This is very important, this D distance. So first of all, you should know that this D we always indicate the distance between the line and the point where I want to find inductance. So here in this slide, I want to find inductance here. For example, I will, let's say, what will be the inductance at this point A. So there are actually two types of flux linkage. Flux linkage we normally note it by lambda. Okay. So flux linkage, there are two types of flux linkage. One is inside and one is outside. Okay. The flux linkage outside means that the flux linkage at this point, between these 2 points, and the flux linkage of this conductor with itself. you can understand this idea like mutual inductance and self inductance, that every conductor has its mutual inductance, and it also have every conductor has its self inductance. So if we will place two conductors together, then we will say that it has mutual conductance. So there are every line has two types of linkages. One is its self linkage and another is mutual. So the linkage which is inside the transmission line, we will call it the inside, and the linkage outside of transmission line, we call it outside. So actually the total linkage is equal to linkage inside plus linkage outside. So here, this formula you have to, actually the linkage inside, how it comes, the mu naught, mu r. I already have explained to you that what is mu naught and what is mu r. Mu naught actually depends upon the type of conductor we use here. So this formula, that linkage inside is equal to mu naught mu r, this is I divided by 8 pi. So this formula is about this equation. You will you see here it derived. Okay, so we are not going in derivation, but we have to remember this equation, only one, this one, and then outside. So linkage outside will be mu naught mu r I divided by 2 pi into natural log of d divided by r. So these two equations which are derived after integration. So I am not going into derivation because in future we have to solve the problems. So here I will just calculate that how the single conductor and single conductor inductance becomes this. Okay, so here I will put the this is the value of inside mu naught mu r I divided by 8 pi. Okay, here I is the current. So this is the flux linkage. So here the outside flux linkage is this. If I will add both of these, then I will get mu naught mu r I divided by 8 pi, the same here, plus outside linkage mu naught mu r I divided by 2 pi, multiplied by natural log of d divided by r. What is r? R here is explained here. It is the radius of that line. So d is the distance at where I want to find the inductance. Okay.
Okay.
Okay. If you want to ask, you can ask someone.
I understand.
Okay. So I will take here. You can see that mu naught mu r I divided by 8 pi plus mu naught mu r I divided by 2 pi. So now you understood that we put these two values in this equation. Then you will get the total flux linkage at this point. So I will take common. You know common, right? Mu naught mu r I divided by 2 pi. I will take common from here, and then inside it will remain, because that 4 multiplied by 2 is 8. So I will just take 2 here, mu naught mu r I divided by 2 pi. I will take outside, then the inside, what will remain? It just remain 4, because these three are outside, and 2 multiplied by 4 is 8, plus the whole thing from this part of equation will go outside. So inside we'll just get natural log d divided by r. So here is, if you know the mathematics, that we can write this 1 divided by 4 is equal to natural log of e raised to the power 1 divided by x, because natural log of e raised to the power e is equal to 1. This did you understand this one, that 1 divided by 4, how it becomes natural log of e raised to the power 1 divided by 4?
Yes, I get it.
It is from the formula of natural logs. So after that, okay, this is the same one, I think. So no, here, so you know the natural log of a plus log of b, we can just multiply, just write as log of a multiplied by b. So it is just like that, log of a plus log of b is equal to log of a multiplied by b. So this is just like that. So I put here d divided by r. You know that log of m plus log of n is equal to log of mn. You know this.
Yes, yes, I know these rules.
Why is e raised to the power minus 1 by 4? Because this is already in denominator, this r. So we just multiply by d multiply by e, d into multiply by e raised to the power 1 by 4. But I put this value in denominator, so I wrote minus 1 divided by 4. So actually what here we have to understand that what is r into e raised to the power minus 1 divided by 4. So this we denote by r dash, r slash. We call it effective radius of any conductor, because we will use this value in numerical, so you must understand this one. So I will we call it geometric mean radius. Normally when you solve the problem, you will see that the geometric mean radius of a transmission line is like, so we will calculate this GMR is equal to R into e to the power minus 1 divided by 4. So basically this equation will become like natural log of d divided by r slash. So what is this? This is geometric mean radius. For example, if someone gives me the radius of transmission line, I will just multiply by e raised to the power minus 1 divided by 4. And through calculator, you will know that e raised to the power minus 1 divided by 4 is 0.7788. So if I will know the radius of conductor, then I will get the value of GMR. I will just multiply its value with this value.
That's for only a single wire?
No, it's for all type of wires. Not for example, I have two wires. For example, here, then the value of r dash is will be also be the same. But this
Okay, I'll multiply it by 2. The r, I'll put it with 2.
what 2?
I mean, how am I going to use this GMR if it's not a single wire?
No, if for example, if in question, in problem, someone tell you that okay, you calculate the single wire inductance, so you must know the value of radius, right? In problem,
Right.
it is given that it is for example 10 millimeter or 20 millimeter radius. So you will just put the value of radius here and multiply with 0.7788, and then put value here. And the distance will be given too. So you will just put the value of distance and this, and then you will get the value of flux linkage. But we are going to find inductance. So I am converting this into inductance, this value, flux linkage. This is not the final formula. Final formula we are going to get in next PPT. I just want you to understand that what is R dash, because if you will not know what is R, then you will never know about the GMR. So we know that this formula, I think you know, it is from the previous semesters, that flux linkage is equal to L multiplied by current, inductance multiplied by current. So from this formula, as already I have find the inductance of a single wire, right? So I will just put the value here and I will get the inductance of that line. I will put the value of flux linkage here and I will get the inductance. How I will do it? I can rearrange this equation like L is equal to, I will divide here. It is multiplying here, so it will come here and divide. So this is the value you can see from here. This I got from previous slide, the flux linkage of a single wire. So I will just put this value here, and then you will see that this I will be cancelled out with this I will put here, and then we get, because this is lambda divided by I, and this I will be cancelled by this I. All the other things will remain the same, because in this equation there are only two values, lambda divided by I. I will put this value here, and then I will be cancelled with I, and then we will not get current in inductance value. So today we know about that the if I want to calculate the inductance, I don't need current. So you must know this thing. I just need to know the distance, the radius, geometric mean radius, and only these two things. I will also convert this in constant. You will see now, because this mu r, we normally say that in general we take relative permittivity is equal to 1. I will put the value of 1 here, and mu naught divided by 2 pi for aluminum, we normally we put the value here and divide by 2 pi, 3.14. I will solve it. I will get 2 multiplied by 10 to the power minus 7. So I will put directly mu divided by 2 pi here is equal to 2 multiplied by 10 to the power minus 7. This is already 1. So I will simplify my formula and I will get the inductance formula here. So this is the inductance formula for single wire. What I need, just the radius of wire and the distance at which I want to calculate the inductance. For example, 1 centimeter away from wire, or 2 centimeter away from wire. Why we need to drive this formula? Because we are using it in all single phase and 3-phase inductances. If you want to calculate the inductance of single phase 2 wire or 3-phase 3 wire, there are different types of arrangements we will study. So you must know, you must remember this formula. You must know that in case of 1 wire, this is the formula. In case of 1 wire, so you just remember this. I drive this because it is for your better understanding. But you have to remember this formula. This is very important.
Okay.
We are going to use it in numericals. You want to ask something?
No, I understand it well. Thank you.
Okay. So now 2 wire inductance. So what we will do if there are 2 wires? Now in the case of single wire, you just put the values in this formula. Very easy. So in case of 2 wire, what formula we use? Now we will calculate here. Actually, for each for each type of demonstration, like single phase 2 wire, 3-phase, and 3-phase bundle conductor, we will see the geometry of the conductors, that where they exist, and then we will calculate the inductance. Because now we see that current is doesn't depending upon inductance. The value of inductance, we don't need current for calculating the value of inductance. So we are just using distances here. So for example, I have 2 conductors. You are seeing on I can also record this. It's also recorded. Okay, so there are 2 conductors. For example, one is here, one is here. R1 is the radius of this conductor. R2 is the radius of this conductor. So this is case of single phase. You know, then single phase we just have 2 conductors, like in our distribution network. From one conductor, current flows like this. From second conductor, current flows like this. You know it well, right? Load is connected here. The current flowing from this side and coming back from this side. This is phase. Maybe this is neutral. So in single phase, we don't have similar radius. You will note, you will see that if you will go outside, you will see that there are, for example, 4 lines, 4 distribution network, 4 lines, for example, 220 volt or 110 volt. So you will see that radius of the neutral wire is less than the phase wire. So that's why I said that the radius of these both lines will be not the same. So radius of the phase line is greater than the radius of the neutral line. So this is R1, this is R2. This is the radius of this line. This is the radius of this transmission line, or you can say distribution line. So as both wires are separated by distance D, okay, I just wrote here, see, it's a correction, I will correct it, it's D. Both wires are separated by distance D. This is the distance between 2 wires. So we apply the same calculation for each conductor as provided in previous slide. As here in previous slide, I have calculated this value. So I'm going to use this value here. So this is in case of single wire, right? So I have 2 wires. So in this, I will use the same formula. here the same equation, L1 is equal to 2 multiplied by 10 to the minus 7 natural log of d divided by r1 slash, this is the effective radius. So this is not the real radius. To get the effective radius, we have to multiply the real radius with 0.7788, and then you will get the effective radius. So here, I will just, for example, I will just put the value of d here and the value of r1 slash. So you know the what is the value of r1 slash, r1 dash, right? How to,
Yes, we're going to multiply this over with the e power negative
yes,
0.25, right?
yes, you can simply, it's very easy here. You can simply just, yes, okay. So this is the transmission, this is the, I was, yes, transmission line for inductance L1. I will see this transmission line. So I will put the effective radius of this transmission line, just multiply the radius with 0.7788, or you are saying that e is power minus 1 divided by 4, and I will get the value of R1 slash. So what about the inductance of another transmission line? It will be the same, that this d is the distance between two lines divided by R2 slash. R2 is the effective radius of this line. So now here what we have to understand. So on this point, you have to understand that in the inductance we are including two distances. One distance is R1, the radius here of this line, and second is D at this point. Because here in this area there are two conductors, so I have to include the effect of both the conductors. By including this distance R1, I get the effect of this conductor. By including this distance D at this point, just we calculate that how to find the effect of this point on this line. You can say like this. At this point D, I will also include this. So I will just add up these and then I will get total inductance. So how to get the total in case of two wire single phase conductor? I will just add up these two values and then I will take common 2 into 10 to the power minus 7 to multiply by 10 to the power minus 7. I will take outside, and inside I will just get natural log of d divided by r1 slash plus natural log of d divided by r2 slash. You got this, right? It's mathematics. So,
Yeah.
so here the same formula I am applying. Natural log of m plus natural log of m is equal to natural log of m multiplied by n. So I will just multiply these two values. Natural log of a plus natural log of b is equal to natural log of a multiplied by b. So natural log of m, natural log of d divided by r1 slash plus natural log of d divided by r2 slash. I will multiply these two values according to the log formula. So d multiplied by d, I will get d squared divided by r1 slash multiplied by r2 slash. So this is the total inductance in case of two wires, two conductors. But I will further simplify it to get the final formula. So how I will get final formula? I can take it, write it like this. So how I got this, I am explaining. I can just write, okay, let me use notation. Okay. If I will take under root of this and then apply square, it will not affect the equation, right?
Yes.
Yeah, it will not affect. So here square and here square, I can take the like natural log of d under root r1 slash r2 slash. I can write like this, no problem, right? You can.
Yes.
Because d, yes, no problem, because d square, I took it as whole square. So you know that natural log of A raised to power x can be written as x into, this is equal to x into natural log of A. I can write like this. So I will just write this 2 value. I can write it here. If I will take whole square, I can write it behind the natural log here. So it will multiply by with this 2. So it will become, yeah, so it will become like 4 multiplied by 10 to the power minus 7 natural log of d divided by under root r1 slash r2 slash. So this is the final formula in case of two-wire inductance. You must remember it. First, you must remember this formula for single conductor. Then in case of two conductors, you have to remember this formula. How to I'm telling you a sequence that how to remember the formulas. So I am telling you, look, there are two conductors, like, so R1, R2, whole power 1 divided by 2. So there is one conductor. So there is only R power 1 divided by 1 or 1. Here two conductors. Here R1, R2 power 1 divided by 2. We will see that in three conductors, R1, R2 raised to power 1 divided by 3. So in this case, you will remember this formula in current slides. But for this here, I will just put the value of, if we will solve problem in next lecture. But here I'm just clearing you the formula and the tricks that how you can remember the formula and from where this formula came. So you got up to this point, you understood it?
Yes.
Okay. So now we are moving to next slide. So inductance of three phase. So now in the inductance of single phase was very easy. We know that there are always two conductors, right? So there is some distance between them. So it is easy. But three phase conductors are a bit complex. Not very complex, but a bit complex. In case of three phase conductors. So three phase conductors, if the distance between each conductor is same, like I am saying that the distance between the A and B here is D. There are three conductors here, A, B, C. Both, this is first phase, second phase, third phase. There are three phases in this transmission line. So you know that these are arranged in a way that they have equal spacing. This distance is also D. This distance is also D. This distance is also D. So in problem, you must have to know. For example, it is written in a numerical problem that all the three conductors are equal spacing conductors, equal right conductors. So in that case, you know that the shape of conductor must be like this. If you will see the cross-sectional view, then it will be like this. So this distance, and this distance, these three distances are same in case of equal spacing. Then we will go for in case of non-equal spacing. Firstly, we will cover about in case of equal spacing. So in case of equal spacing, we know that from the first slide that L is equal to 2 multiplied by 10 to the minus 7 natural log of D divided by R dash. This is case of single. This is case of single conductor. So how many conductors here are? Three conductors. So it's these are, if distance is same, then we just add these three inductances and get total inductance. It's very easy. You just find the inductance of A, put the value of D here and the R slash, and then put the value of this D here, and then R slash R radius of this conductor, because distance is same everywhere. So you will just put the values here. So this is the equal spacing. But in mostly numerical problems, we don't get equal space conductors. So what we will do? So first thing that in case of equal in case of non-equal spacing between the conductors. This you got it right? This up to this slide, you understood it?
Yes, we're going to يعني
You
make the three, get three L's and just add them together.
say it again, please.
In this situation, we're going to get the three L's and just add them together, right?
Wait, I couldn't understand. Can you repeat? I cannot hear.
In this, if it's equal spacing, can I just get one of them and multiply it by 3? Get the inductance of one only and multiply it by 3 if they are equal spacing.
This is no, actually, in case of this, yes, you will just in case of equal spacing, yes, you can. But in case normally in problems, I saw your the problems from your notes. They are about unequal spacing.
Yes.
Yes, so we are going for unequal spacing.
Okay.
So in unequal spacing, the transmission line will be different. I am explaining here. It will be okay. Now, what is the problem? Firstly, we have to understand that in problem you will see that in sometimes it is written that equal spacing conductor. Then it's very easy formula. But in case it is written that these are transposed line. This is transposed transmission line. Then formula, then the equation will be a little bit different, not very much. So you must know about it that in the problem, firstly, you have to read the problem and you have to confirm that it is written that transposed line, transposed transmission line, or transposition of transmission line has been done. Normally, in our power system, we always transpose our transmission lines in case of unequal spacing, because unequal spacing will disturb the voltages at the receiving end. You know, for example, as you know that the if the inductance of each line, because here we are talking about three phase, right? For example, the voltage of normally in a three phase transmission line, the voltage of the receiving voltage and sending voltage, you can say that the receiving voltage of all the three phases are same, or sending voltage of all the three phases are same. But what happened if in case of unequal spacing, the inductance of each transmission line will be different? So that's the problem. So at the receiving end, we will get different voltages, but we don't want that. For that purpose, we don't want our receiving end the voltages are different. For example, in phase, I'm just confirming here. You can see like this. For example, this is I can write. For example, this is line 1, this is line 2, and this is line 3. Now I will calculate the inductance of each line. For example, inductance of this line is 10. That's the this is like we say that okay, 50 millihenry, for example. This, for example, is 30 millihenry, and this is 40 milli. What is problem here? So actually, you know that our voltage drop depends upon inductance. If there is more inductance, then I will get less voltage here. For example, it is 11 kV line, or we can say, for example, it is the 33 kV line. I am getting 33 here. Maybe I will get 28 here. We can say that I will get, for example, 24 here. So the volt not, it will not be too much big difference, but normally I want you to understand that we want all phase at 33 kV, but in case of in case of unequal spacing, because here distances are involved, so distance of these two conductors will be d, and distance of this conductor from this conductor is d2, will be different, not like in the previous slide. So we will get the different voltages at the receiving end. So to reduce this effect, we are going to transpose our transmission lines, because inductance depends upon the distances, distance from this conductor to this conductor and distance from this conductor to this conductor. So if, for example, I will put this conductor, for example, I have 3 kilometer transmission line. So in second kilometer, I can change, I can put this, I can I can transfer this transmission line here on this pole, and I can transfer this here. And after again 1 kilometer, I will just change it. So this is called transposition. It will be better. I will explain it in diagram. So, so this transposition is done to avoid the voltage disturbance at the receiving line. So it will equalize the voltage if we will do the transposition of each conductor, because inductance depends upon position, and position means the distance from conductor to conductor. So here I am explaining, this is transposition. For example, here of this conductor, for example, this conductor, we have seen the formula. Formula depends upon the d and radius. So if the radius of all the conductor is same, the d will be the different. This conductor have two d's. Here one d and here two d's. So it will add the effect of this d2. So what we will do, we will put this conductor for 1/3 of length here, then 1/3 here, then 1/3 here, and then we will put this connector 1/3 here, 1/3 here, 1/3 here. So the total inductance should remain the same. As you know that we in transmission lines we calculate the inductance in terms of kilometers, that 20 millihenry per kilometer or 15 millihenry per kilometer, or even less than this. So we have for example, this line is getting 10 millihenry here. This is getting 20. This is getting 30. So this will get 20 here, and this same transmission line will get 30 here. So in a matrix, we will say that the values will equalize and the voltage will not disturb at the receiving end. This is called transposed lines or transposition. Do you have any confusion about this?
No, I understand.
Okay. So this is the formula in case of transposed line. So we will. This is the formula DAB. Now this formula can be the same. You will say that like from this, it will be the same formula. This. You will see here that if I will put these d3 values here, it will be the d cube, right? And here, if it will be the d cube, then this 3 will be the cancel out with this. Okay, I can also derive this formula from this value. So actually the distance, we are going to include that distance A to B, then distance B to C, and distance C to A, raised power 1 divided by 3. The distance between A to B, and then B to C, and then C to A. We just have to calculate, we know about these three distances. After that, we will put this value in our formula, and then we will get the inductance. As the radius of each conductor is same, so the effective radius will be R. In case of transposed line, the radius of each transmission line is same. So this is DAB. D, B, C, B to C distance, and then C to A distance. If you will closely watch this equation, that it will be the similar. Let me go towards this. You can copy this, and then we will compare it with this. For example, I am comparing these two formulas. You will see that look, it is the same formula. You just have to remember this one, that 2 multiplied by 10 to the power minus 7 natural log of d divided by r slash. But what happened here? Here are three distances, not one. So we have to include that these three distances, A to B, B to C, and C to A, these three distances. So 1 divided by 3. Here is 1 divided by 1, so you cannot see. Now this is the case of single conductor. Like now I will compare it with the two conductors formula. This is the case of single conductor. This is a case of two conductors. This is a case of three conductors, unequal spacing. Okay, transposed conductors. So you will see here that in case of one conductor, I am getting the power on radius. Um, so the single conductor will be a bit different than this one. Single conductor. So this is R1 slash R2 slash raised power 1 divided by 2. But in case of these two conductors, this is the two conductors formula, and this is about the three conductors formula. That you have to know, you have to put all the three distances here. You have to know the distance between A to B, and then B to C, and then C to A. So if you remember the basic formula, you can compare each of them, and then the remember you will, it will be easy for you. Like for single conductor, you have to just put one distance. For three conductors, you have to put three distance, but you have to raise the power 1 divided by 3. For two conductors, because there is only one distance between two conductors, there are not several distances. So I will just put one conductor here, one distance here. As the radius of both conductors is different, so R1 slash into R2 slash raised power 1 divided by 2. If the radius of both conductors is same, even in the case of two conductor transmission line, then it will be the formula. You will see that R1 into R2, if both are same, then square will be cancelled with under root. Then it will become again R slash. So the basic construction of formula of these equations is same. You just have to remember, okay, in case of single conductor, it is 2 multiplied by 10 to the minus 7. Okay, I just multiply this with the value 2. I will get the two conductors. 4 multiplied by 10 to the minus 7. But problem is here, in case of two conductors, if radius is same, then the formula, I just multiply it with two. This is single, this is two, this is three conductor formula. So in case of single, in case of double, I will just multiply this formula with 2. You will say 2 into 10 to the power minus 7, multiply by 2, 4 into 10 to the power minus 7. But the radius is different. If radius is same, then it's r square will be cancelled out with under root. The formula will be same, 4 multiplied by 10 to the power minus 7 natural log d divided by r. So in case of three conductors, equal spacing, it will be the d cube will be cancelled with 1 divided by 3. Now here in case of three-phase conductor, the formula is a bit different. If the radius of A conductor, B conductor, and C conductor is same, so that's why it's r cube instead of 1 divided by 3. It is cancelled out with the value. That's why it is r. Otherwise, if normally it doesn't happen, but it happens that the radius of each conductor is different. Then it may be r1 slash r2 slash r3 slash raised to the power 1 divided by 3. So you understood the basic construction of formula of this equation.
Yes, I understand. Thank you.
So you just have to remember these three. You can drive one equation from another, from this. You can also drive this, but I am not going in derivation. You just need to remember for single conductor, for two conductors, multiply by 2, different radius r1 slash r2, same radius r. So same here. So I'm going to delete this from this part. So until now, if you have any question, you can ask me.
Thank you. I understand.
You really understood?
Yes, really.
Okay. Actually, because I don't know my English, whether you can understand it or not. I don't know.
No, no, it's fine. I understand it. Don't worry.
Okay, thank you. This was single wire inductance. After that, two wire inductance and equal spacing. We have done this. Three-phase transposed line. We have also remembered this formula. Yes, formula. Okay. Now bundle conductor. Now you know that bundle conductor means we are adding one conductor. Like here we were watching that